So any question, if it comes on color, will be high definition, crystal clear. Please see, there can be only two reasons for the color of any D block element. DD transition is the easiest one to figure out. The other one is charge transfer, which are of various kinds. So first, let's just clear what is DD transition here. You can see you have some unpaired electrons here. You have three unpaired electrons. One of the electrons can just get excited because of this D transition, because of this excitement. There is some energy it has absorbed and it goes to the excited state. That is not the reason for the color. It has absorbed some energy and has gone to the excited state. That, my dear, is not the reason for the color. Then what is the reason for the color? Well, the reason for the color is when it comes back, it emits some energy, and that energy lies in the visible range. Now, there is very interesting thing which is possible from here, which is the concept of the complementary color. Okay, check. A metal complex must contain an unpaired electron for a DD transition. So this is a non-negotiable. If you have a D block element in a complex, in a coordination compound, showing color, and it has an unpaired electron, then the reason is DD transition for sure, right? So corresponding wavelength gives the complementary color. So due to the absorption of some specific wavelength in the visible region, you will see the excitement, and the transmission or reflection of the light with the rest of the wavelength. Check this out. This is what we mean by the complementary color. You can write 6 colors like this. You miss VIBGYOR, miss the I. Remove the I. I mean, you can remove I as in the ego, and you can remove I as in the indigo. So we can write V, I removed, BGYOR. So if there is a metal which has absorbed violet color, what is the color you will see? You will see the complementary color. What's the complementary color? Just the opposite. So you're supposed to make a circle in a nice way. Please see, you can make a circle, divide it into how many quadrants? You can draw like this. Right? V, I gone, B, G, Y, O, R. So if violet color is what is absorbed, yellow color will be the color which will be visible. Okay, which will be, if this is absorbed, this is what is getting transmitted. Similarly, if green or blue-green is the color which has been absorbed or which is being observed, if this is the observed color, if this is the observed color, blue-green, then red-orange is the wavelength it is trying to absorb. Ulta, opposite. Okay, I hope the questions which are possible from the complementary color is clear. Whatever color is visible, its complementary color has been absorbed. How do we know which is the complementary color which has been absorbed? We know it from this whole complementary circle or the chart that we have. Please observe. So complementary color is generated from the wavelength left over. Keep that in mind. This will be very useful. Going ahead. What will be the color of the complex if the ligand is absent? If there is no ligand, what will be the color? Okay, this is an interesting question. So in the absence of a ligand, the crystal field splitting does not happen. That means DD transition does not happen. And if DD transition does not happen, it should be colorless. But check this out. If you have this option of titanium, which is 3+, chodo T, so titanium, chodo T, that means 22, 4s2, 3d2. So you can see X is equal to +3. 3 will go here, +3. So X is equal to +3 means there is just one electron. Only one electron we have, and we are saying there is no possibility of the DD transition out here. It is just having one electron when it is present like this in the form of TiCl3, where there is no ligand. The complex is now existing like TiCl3 plus 3 oxidation state here also, and no ligand, then you're not going to show any DD transition. But in the complex, we have one electron, so it can get excited. You can see that here there is DD transition possible when it is in the complex, but now when the ligands are absent, no DD transition. Point to be noted, ligands are important. Also check when we have copper sulfate dot 5H2O. This is the hydrated form, which is blue in color, but when there are no water molecules, it is white in color. Again, you should know that copper sulfate is nothing but a complex. Are we aware of this? What actually is, you have copper out here in what oxidation state? Copper 2 plus. Are we aware of that? Doable? You have water molecules OH2O, which are going to act like ligands. Okay, OH2, and you can also see the hydrogen bonding, which with, you can see oxygen is here. So I am writing OH2O in this way. Let's just write it above. Cu 1, 2, 3, 4 OH2, OH2. So you can see the presence of the ligands here. What are the ligands? There are 4 water ligands. Imagine another water molecule which is present in the form of the hydrogen bonding, OH2. This much is okay. Then another hydrogen bonding is there with the oxygen of the sulfate. So this is how it is present. Please check what kind of a complex does it appear to be like. It appears to be like a square planar complex. How many hydrogen bondings are here? 1, 2, 3, 4. The hydrogen bondings are 4. The coordination number is 4. The complex is not sp3 but dsp2. The copper here has water molecules which are ligand. That is why it is blue in color. The anhydrous form, even though has +2, copper 2 plus means, you remember copper was 4s1 3d10. So 2 electron means 3d9. There are unpaired electrons, but still no color. Clear? Right now, you have a question coming up. Check, this is a JEE mains question. From the ligands, that means you have what kind of ligands? Here you have Cl ligand and ammonia ligand. Ammonia, how many? 3. How many? 5 ammonia ligands are here. Here 5 ammonia and 1 water. Here 6 ammonia. Okay, out of chlorine, ammonia and water, can you tell me the strength of the ligands? I think we discussed about the strength of the ligand in the previous session. What is the strength? Which is the strongest one? You remember the halide ligands were the weakest ones. All the halides were the weakest relatively. Then the oxygen ones were the second weakest. And the nitrogen ones were the best because the Maya towards the electron was least relatively. Right? So here 6 ammonia wins. This is the order of the strength of the ligand, that means. So if this is the order of the strength, can I say that more there is the strength, more is the splitting? Pairing was favored. So the splitting energy would look like this. The maximum energy of splitting is here. If E is maximum, E is equal to hc by lambda. So E is inversely proportional to lambda. That means if E is more, lambda is less. Please check. Right? So wavelength is least here. Wavelength is least where you have 6 ammonias. So you have to know where absorb light in the visible, the correct order of the wavelength of the light absorbed. This is exactly what we have to find out. So here E is going to be relatively in between, and here the E is going to be minimum relatively and lambda is going to be maximum. So the first one, please check, will have the maximum lambda. If first one has the maximum lambda, you have decoded the question. That means the question has been decoded. The whole thing was that ki bhaiya, strength of the ligands is what we should be aware of. So these kind of questions are a collaboration of the color and the strength of the ligand, and I'm sure you're going to get full 4 marks in these questions. Okay, let's move ahead. Okay, try this one. Octahedral complex of a metal ion M3 plus with 4 monodentate ligands. There is L1, there is L2, there is L3, there is L4. They absorb different colors. There is red, there is green, there is yellow, and there is blue. Okay, great. Respectively, the increasing order of the ligand strength. That means we need Rahul Mishra is visiting Uncle Xavier's garden. RMIVUXG. Do we remember visible is written in such a way that this is your IR, infrared, and this is your UV, ultraviolet. So write it like this, VIBGYOR. And we know that red has the highest wavelength. So this is the increasing order of the wavelength. We have been studying since class 9th, class 8th, class 7th. The sign of the danger is red in color. The stop signal of the traffic is red in color. What's the reason for that? Because the red color can travel longest. The wavelength, that means, is highest. So yeah, this is the order of the wavelength. What do you have to find out? You have to find out the ligand strength. So from the wavelength, can we talk about the ligand strength? If wavelength is highest here, VIBGYOR, violet we don't have, indigo we don't have, blue we have. The wavelength is minimum here. That means energy is maximum here. That means the strength of the splitting is maximum here. That means the strength is maximum here for L4. L4 maximum, there you go, you figured it out. And red one was having the highest wavelength. That means energy is minimum. That means the weakest ligand is L1. So yeah, there we go. That's fitting in everything that we are trying to apply using the concept of wavelength, energy, and the strength. So B is B for bang on right answer. Great, great. You guys are going fantastic. Which of the following complex ions is not expected to absorb visible light? So Ni2 minus. Chodo TV car mango fico need. That means you have 3D8 4s2. And because you have out here x minus 4 is equal to minus 2, x is equal to plus 2. So 2 electrons will go from here, and you will have the 8 electrons in what way? Because it is along with cyanide, they will be sitting in a paired manner. If they are sitting in a paired manner, will it show any kind of splitting? DD transition? Huh? Diamagnetic and colorless? Correct. Okay, so there you go. But you can check for Cr3 plus, iron 2 plus, and Ni2 plus here with water as well. And you will know for yourself why we are going with option A here. You can check for the rest as a part of your homework. Next one, the correct order for the visible wavelength of absorption in the following visible region is. NH3 out of NO2 and NH3, you know that we have NO2, NH3 and water. This becomes the order. NO2 minus NH3 and water, this becomes the order. Now, if you know this is the order, then we can decide the stronger it is, the higher will be the E, the lesser will be the lambda. So, wavelength is going to be least for the NO2 minus, which is in option A and B both. So, we need to decide from now ammonia. The water one has the highest lambda because the energy is minimum. This is the weakest one. So yeah, A becomes the answer for this question. Okay, these kind of question, now I'm sure you're through with these kind of questions. They can be collaboration of color with the strength. So I hope you're sorted. Okay, let's now proceed to the other one which we have not discussed. And I think all the old students also will have a great time here because this we did not do previously also. But I am expecting a question this time from charge transfer spectra. Let's do it nicely right now. Charge transfer spectra are of various kinds. The transition in which the electron is transferred from one atom to another, like it says, there is going to be some transfer, like the transfer of money. So from bank, the money has been transferred to your account. From somebody's bank to somebody else's bank, there is a transfer. So here also is going to be a transfer. Now, what kind of transfers are possible? Like I said, there are two transfers that we shall be studying. So charge transfer transitions are also considered as internal redox. So this transfer is nothing but a redox. There are some electrons which are going. Loss and gain of electrons are what is redox? So the charge transfer is nothing but the redox reactions which are happening within. Okay, sometimes you borrow money from your own brother. That kind of a transfer is what we are talking about. That's it. There is this borrowing which is taking place. Okay, now let's see. So the charge transfer can be three kinds. One is the ligand metal charge transfer. So whatever is written first, that kind of a charge transfer. Ligand to metal, metal to ligand, metal to metal. Okay, please see how have I written it? The three kinds of charge transfers that you have. You have, observe, please see, ligand to metal, metal to ligand, metal to metal. CT is common for charge transfer. Are you good? Okay. Now, see the first one coming your way, ligand to metal. Now, what is going to be happening is, we are going to provide electron from the ligand to the metal. Metal is having a positive charge. So, if I talk about this ligand to metal charge transfer, electron donor is ligand and the acceptor is your metal. Now, how is it different from DD transition? Where do we know that this ligand to metal charge transfer is taking place? Charge transfer occurs from ligands filled molecular orbital to metals empty or partially filled d orbitals. So it is very interesting. It is easy for us to note that wherever you will see the metal having very high oxidation states, either +7, +6, +5, very high oxidation states, that's the hint for us that it can have what kind of the reason of the color. The reason would be the transfer of electron is happening from the metal. Like what you see for KMNO4, potassium permanganate is deep purple in color. Like you said, you only told me the color of the potassium permanganate now. How is the color coming? You have these you have O4 minus, KMNO4 minus. How does the structure looks like? This is how the structure looks like. So these oxygen with the minus is providing the charge to this manganese, which is in X minus 8 is equal to -1. So X is equal to +7. You can see it's not having any electron, D, zero electronic configuration. The metal has a very high oxidation state. That's a hint for us. So this is what that can be asked. MnO4 2 minus, you can see X minus 8 is equal to minus 2. So minus 2 plus 8 is plus 6. So again, like I said, this is the hint for us. Here we have manganese having one electron, but the reason of the color is because of such a high oxidation state on metal. It's the oxygen, two oxygens with the minus charge, which are going to transfer the electrons responsible for the green color. Same here, K2Cr2O7, potassium dichromate, or Na2Cr2O7, sodium dichromate, orange color. Why is that orange color? These are the ones which are there in your DNF block. Why is this orange color? The metal, you can see, is in high oxidation state, plus 6. Yeah, that's the hint. And no electron, the d electron, the d orbital is empty. There is no electron in d orbital. All the electrons are gone. The oxidation state is plus 6. Here it is X minus 8 is equal to minus 2. So minus 2 plus 8, CrO4 2 minus. So again, here also you have plus 6. It's in highest oxidation state. This one is sodium chromate, is yellow in color. Please check. Interestingly, there is also one thing that you must know. Manganese out here has zero oxidation state. So its d orbital is empty. Right? But this student say sp3. The p orbitals are not getting filled. Please mind you, the hybridization is not sp3. What gets involved are the 3 orbitals of the d and 1 s, giving it d3s hybridization, be it for MnO4 minus or Cr2O7 2 minus or CrO4 minus or MnO4 2 minus. All of these has D3S hybridization. That's also a question that can be asked. Are the reasons for the color of all of these, which are very important from the NEET perspective, they are also important from JEE perspective. The question has come, in fact. Let's see. So ligand to metal charge transfer, MnO4 minus, you can see purple in color, MnO4 2 minus, this is potassium permanganate, this is potassium manganate, green in color. The colors are also important. You can check. The reason is ligand to metal charge transfer. These minus that you see out here are transferring the charge responsible for the color. So is with potassium dichromate and potassium chromate. Okay. The reason of the color is the ligand to metal charge transfer. This was a question asked in JEE mains. Please check. The color of KMnO4 is due to, what will you say? What's the answer? That's right. Now you know it. Now you know it. Okay, that's a direct question which is possible. So free marks for us if we remember what we are doing in today's class. Next, metal to ligand charge transfer, not very likely. If the examiner really wants to set a very hard paper for you, the question can come from here, because color is a part of your syllabus. So yeah, it's not that it is highly improbable that you might not get a question from here. So that's why I'm doing all the charge transfers with you. Let's see here. What's going to be happening is metal to ligand charge transfer will be responsible. There is going to be an electron donor, which is the metal, and electron acceptor, which is going to be the ligand, and metal to ligand charge transfer will be responsible. How do we know where it will happen? Charge transfer occurs from the filled metal's orbital to empty orbital of ligand. How do we know that? Where is it? You will see the metals are going to have zero oxidation state, either +1 or +2, low oxidation states. Ligand to metal, high oxidation states. Metal to ligand, low oxidation states of metal. That means metals are having electrons that can be donated to the ligand. Examples, HgO, this is the important one. You can see Fe, Fin 3. Can you tell me what this fin is? This is something that I have already done with you. I would love to hear from you. What is this? Fin, P-H-E-N. But the reason, see, when the reason can be DD transition, it will be a DD transition, the easier one which is happening. That is not an electron transfer which is producing the color. That is a synergic bonding which is happening and leading to the formation of a pi bond. This is an internal electron that is transferred, just like a redox chemistry which is happening. For example, if I talk about this phenanthroline, there are nitrogens, you will see there is this benzene. I think I drew it for you, or I've shown it to you, I'm sure. These are like 3 benzenes, but heterocyclic nitrogens. They are going to accept electrons. So metal to ligand, these ligands are going to accept, and this Fe3 plus. Here you have no charge on fin, okay? So iron is in 3 plus oxidation state. HgO is the classic example of this, where you see a color because mercury has transferred an electron to oxygen. That is why there is a color. Or FeACAC. What is ACAC? Can you tell me this one also? Let's think. I have given you ACAC, this one, while teaching you that active methylene compounds. So think of one of these existing like an enol form, O minus like this. This is how it mostly is going to be existing in, like I said, because it becomes stable. So O minus, this is FeACAC, acetyl acetonate, and this is going to be a bidentate if you are going to take the O having a minus. It can accept electrons from the iron and give you the color. Okay, so these are the three compounds which can be asked. Okay, mostly if you want to remember, this is the one that can be asked a lot, because this is also a part of your practical inorganic chemistry. None other is a part of your practical inorganic chemistry. And the third one, which is absolutely a part of your practical inorganic chemistry, is this one, metal-metal charge transfer. If you remember metal-metal charge transfer, where to see it? Hey, it's easy. The excitation and subsequent transfer of electron from lower oxidation cation to higher oxidation cation. So you should have, let's say, Fe3 and Fe, there is Fe3 plus and Fe2 plus, both in one complex. Do you remember what complex I'm talking about? A complex having iron 3 plus as well as iron 2 plus, both. If that is the case, see the lower oxidation state cation to the neighboring higher oxidation state cation. The electron transfers is happening between the two metals only, and hence the metal-metal. That means you need to have two metals. And there is one very important metal-metal complex, the Prussian blue complex of ferriferrocyanide. This is ferriferrocyanide. This is a part of your detection of the Cn minus in the practical organic chemistry, POC. You do this test. You add freshly prepared iron chloride. If you want to test Cn minus, you make the Lasange extract. If there is a organic compound containing cyanide, you first convert it into NaCN, you add FeCl3, you will get, and the complex which is formed is having oxidation state iron outside one, the counter ion +3, the inner one +2. So the reason of this Prussian blue is because of the metal-metal charge transfer. Okay, so here you have K4FeCN6. You can see the color is Prussian blue. There is also another one. Please see, this is Turnbull's color, Turnbull blue, which is having opposite. Iron here is 3 plus, iron here is 2 plus. The inside iron is now 3 plus. Please check, here it was ulta. Here the outside iron was 3 plus, the inside iron was 2 plus. The outside was 3, the inside was 2. 3 and 2. Here it's ulta. Turnbull color, outside is 2 and inside is 3. These are the ones where you will see metal-metal charge transfers. Is it clear? Please tell me. These are the possibilities of the question. One is a Turnbull color when outside iron is in +2 and inside iron is in +3. We call it Turnbull color. When outside iron, ferrocyanide is your Prussian blue, which is a part of your practical organic chemistry. Ferrocyanide is also possible, and that is Turnbull color. Okay? Yeah. Now, more questions are possible from the color which can directly be asked. For example, the gemstone colors. So I don't know how many of you believe in the gemstones and the gemstones can change your life. Not without you doing the actions. You have to do the actions in order to make the gemstones work. Well, I don't know actually if they work or not. I've never put one on my hands ever, but I have recently purchased one stone, which is the pyrite stone. I don't know if you know that fool's gold. Fool's gold is iron pyrite. So it's an iron sulfide. People call it fool's gold because it's golden in color. It's glittery, and that proverb, that idiom that goes like all that glitters are not gold, comes from this fool's gold only because it glitters but it's not gold. Okay, so here you go. Let's talk about now the gemstones. Ruby is the first gemstone, guys, coming your way. Beautiful ruby. Check the color. You might miss the color, but because you have such powerful visuals in front of you, I'm sure ruby's color will not skip your mind now. Check the color. Yeah, Aditya, these are just NCERT examples that I've got. Here, please see, direct question from gemstone has come. First, we are doing ruby. Ruby is actually aluminium oxide, Al2O3. It contains some Cr3+, very little, 0.5 to 1%, randomly distributed in aluminium 3+. So you have chromium 3+, here in aluminium 3+, and chromium 3+ means chodo TV car. 3D, 4S1, 3D5, 5, 1 from here, 2 from here. So it will be 3D3. That's what is written. So there are 3 electrons. So the color shown by ruby is due to the DD transition that we say. Both aluminium is also 3+ and Cr is also 3+. So the reason here is simple. The electron, the DD transitions which take place. Okay. Chalo, moving ahead now. Emerald. Do you see the color of emerald? Wow. I mean, look at that. Look at that. This is so beautiful. Just looking like a wow. Just looking like a wow. Check. I love the colors. How nature is so beautiful. It amazes me at times. That's the beauty of life. There is so much to explore. It's all happening by itself. This green color, can we figure out why is this green color? Let's check. So you can see emerald, it transmits light in the green region. You see it as green in color. The reason might be, what do you think will be the reason? What is emerald having? I directly have a question for you after this. With what is the color in the emerald? I think I have not kept the... So again, the reason is the same as what you have seen. So these are the ones that I have directly picked up from your NCERT if you check. So beryllium, aluminium, silicates actually are emeralds if you would check there in your NCERT. So it's also called mineral beryl. So this, wherever you see the term beryl, that means there is beryllium involved here. Okay, so beryllium, aluminium, and also silicates are there. Some trace amounts of chromium is also there, which is responsible for the color. So this is another question which is possible. It transmits light in green color. That's why you see the color. Okay, now you can see the question that was asked in JEE Mains 2019 from here. Let's check this question, guys. So, are we clear? The gemstone ruby is having Cr3 plus ions occupying the octahedral sites of beryl. The moment you see beryl, this is for ruby? No, this is for emerald. This is the question indirectly asking that box which is there in your NCERT. The color of the ClNH352 is violet as it absorbs yellow light. So can we talk about this again, the curve out here? So VIBGYOR. It is saying it is violet in color because it absorbs yellow light perfect. It fits our circle, if it fits our wheel of color. Let's call it wheel of color. The spin only magnetic moment of Fe2 plus and Cr2 plus are nearly similar. Huh? The spin only magnetic moment, both are water out here, H2O and H2O. So chodo, TV, car, mango, feet. D6 we have with water. So no pairing, 1, 2, 3, 4, 5 and no pairing. That means 1, 2, 3, 4, 5 and 6. And Cr2 plus if we are talking about, chodo TV car, D4 that means we have with the 2 plus, D5 and 4s1. So 2 electron, 4 electrons we will have. Here also we have unpaired electron 4, here also 4. This is also correct. Okay, we had to find the incorrect one. The spin only magnetic moment here of nickel with a 2 plus charge, that means chodo TV car mango ficoni D8, that means it will have 2 plus charge, 2 electrons from there going out. All of these are weak, so we will have no pairing. 5, 6, 7, 8, 2 electrons, yes, it will come out to be 2.83. So D is also correct. We had to find incorrect. So you are absolutely right. A becomes the answer to this question. Is it clear?